Hi, I'm Samir. I'm excited to share my recent work on secure computation using function secret sharing over rings. Nonlinear functions are essential to secure computation. This is a quick study I've done where you take a very simple neural network architecture and to train it using secure computation. And as a function of the depth of the network, you can see that the relative error goes up. In other words, if you try to train deeper and deeper networks, the errors start accumulating, and that leads to poorer and poorer network accuracy when you're trying to train inside secure computation. So this is just one example of normalization function or functions which improve the stability of neural network training. And this is going to be the focus of this work to actually study lookup style protocols, like can they actually be feasible and practical for nonlinear functions. Most of this work actually draws its benefits from this new primitive called function secret sharing, which was present in Eurocrypt 2015. What function secret sharing does is very similar to Shamit's secret sharing, where instead of sharing a value, it tries to share a function into many different shares. And each of these functions can be locally computed. And it has three properties which define what a function secret sharing scheme is. The first one is just the sum of the shares evaluated at each individual point, add up to be the function value. And the other two properties are succinctness, which is that each of these functions should be really small. Otherwise, you could have trivial function secret sharing schemes, such as sharing the truth table of the function f. And then the other property is the hiding property, which is the share should reveal nothing about the function f. Recent advances particularly have looked into this class of functions called distributed point functions, which are effectively defined by two parameters. They are point functions in the sense they have a non-zero value at exactly one single point, and everywhere else they are zero. These usually have two algorithms defined to them. So first one is a generation algorithm, which actually takes in the two values that define the function and outputs two keys. And then the second part is an evaluation algorithm, which actually takes in each of the keys and an evaluation point, and they would evaluate the function at that point. And in particular, they would evaluate a share of the function at that point. It's a little misleading there. One other related sort of algorithm, which can be seen as just a union of evaluation at many points, is the eval-all algorithm, which evaluates the function at every point in the domain. So there have been some advances in improving this over just a linear complexity algorithm of evaluating at every single point. A little bit about the overall setup of this MPC protocol work is we are going to be working in a three-party asymmetric protocol setup. In this, you have two parties, P0 and P1, who actually do a 2 out of 2 secret sharing of the input. And then there's a third helper party, P2. And the function to be computed is one of these nonlinear functions which we have talked about. Since it's a lookup style protocol, it's agnostic to which function we are really looking at. All the data is actually operating over this ring 2 to the power k. And it's also, Well, in terms of the corruption model, we look at a single corruption model, so only one of the three parties can be corrupt, and we look at both semi-honest as well as malicious corruptions. So particularly given that it's an asymmetric protocol, the corruption could be in one of the parties, P1 or P2, P0 or P1, or it could also be corrupt party P2, and we have to handle these two cases differently. So let's take a quick look at the semi-honest protocol. The semi-honest protocol is very simple. It's a PIR style lookup protocol. And so on the top, we have the inputs, which is secret shares of a secret A. And on the output, we want the value of the function f of A. So the protocol essentially has three simple steps. So the first one is the party P2 actually first has some shared correlated randomness, R0 and R1, with party P0 and P1 respectively. And then the combination of R0 and R1, which is R, so the reconstruction of R0, R1, which is only known to P2. P2 uses that to actually generate DPF keys for this random value R. The DPF keys are then shared with the two parties. So K0 and K1 here are actually the two keys which are shared with parties P0 and P1. So the final part of the first step is actually P0 and P1 reconstruct the value X, which is R minus A. So it's just a shift. And then P0 and P1 run eval all on all their keys and shift the output vector by X. So which is the reconstruction R minus A. And then finally, they perform a dot product of the shifted vector with the database DF. And now this database is just a database which can be publicly constructed, but it's available to P0 and P1, which contains all the values. So this is very similar to the PIR style database. Like you have a public database, and then the eval all allows you to actually pick the appropriate entry from this database. There is a few more details to this protocol, which I'm skipping, which are presented in the paper, but effectively, this is essentially the blueprint of the protocol. With that, I'm going to jump into the next part, which is really the more interesting part of this work, which is how do you make this protocol maliciously secure? So in particular, I have the same components here. Like, so we have the generation, R0, R1, and then we have the other parties, P0 and P1, which are actually doing the two-party computation. So there are two main challenges when we try to make this protocol maliciously secure. So the first one is if one of P0 and P1 is actually malicious. Note that we have the second part of the protocol is just purely a two-party computation protocol between P0 and P1. So this almost, so the first challenge here is actually that how do we ensure the correctness of the two-party computation when one of P0 and P1 is corrupt? I'll come to it, how we solve this challenge in just a minute. But the second challenge is what if P2 is actually corrupt? In which case we have to ensure that a whole bunch of things. So the first one is that the DPF keys actually correspond to a point function. Second one is that the shares of R, which are presented, are actually corresponding to the index of the above DPF. Like if the DPF is a distributed point function, then R is that point. And then the final one is the secret shares are over Z to the power K, and most known prior techniques actually operate over fields. And so how do we solve all these three challenges? So the first one is actually fairly straightforward. Since it's a two-party computation problem with effectively a dishonest majority because one party could be maliciously corrupt, we use a speeds 2K style secret sharing scheme to build this foundation. So in particular, each secret value has three components, which is the secret, the share of the value, a share of the MAC, and then the MAC key, like, or the share of the MAC key. And then throughout the entire the computation, we'll have the invariant that the MAC and the MAC key, the MAC and the shares of the secret satisfy this relation. One other thing to note here is it's really interesting that when we have a distributed point function, the MAC of that distributed point function is also a distributed point function because it will be non-zero at exactly 1 point, which makes it possible to actually secret share both the value, the shares of the distributed point function for the actual data as well as for the MAC. So that's pretty much the first, addresses most of the first challenge. This is a very high level intuition. But the second challenge is the more interesting one. So how do we actually verify that the DPF keys correspond to a point function as well as they correspond to the right point function and so on? So here we use the standard blueprint of sketching schemes. Like how do you verify sketching schemes in the seminal paper by Boyle et al. In CCS 2016. So the first part is to actually construct a linear sketching matrix. And here we have to actually have 4 different rows in this matrix as opposed to 3 previously. And the way these entries are chosen, that the first 2 rows are effectively independently randomly chosen from a sampling space. And then the third one is actually the constraint one, like A3I is actually just the product of those 2. And the fourth one is just a fixed constant. It's actually that. And we'll see in a minute why we do this. And then the second part of the sketching scheme is actually P0 and P1 run the eval algorithm on the keys they receive. So they actually get these 2 vectors y, my, which are the expansions. And then they compute these few values like Z1, Z2, Z3, Z4, as well as Z star. And they're named in such a way that Z1, Z2, Z3, Z4, if we look down at this expression here, it has, there are 3 parentheses. Each of them have their use here. So the first one, actually Z1, Z2 minus Z3 actually ensures that it's going to be a point function. The second term here ensures that the index of the point function actually corresponds to the secret shares of R, which are supplied. And then the final lower term actually corresponds to the fact that you can have the MAC on these values to verify with the MAC provided by the party P2. So that's pretty much the entire blueprint. If we dig deeper into why this approach works, we really go to the heart of this work, which is when we have check such as this, Z1, Z2 minus Z3 is equal to 0. If we expand it, we get an expression like this. And this expression really allows us to do a verification with high probability because of this lemma known as Schwartz-Zippel lemma, which applies over finite fields and allows us to ensure that, like, if you have a random sampling of AIs, and this is a bilinear polynomial, you can ensure that if it is non-zero, then with high probability, you'll get a non-zero value. And so the verification actually enables you to check whether the polynomial was zero. So in this work, what we do is the core result is really a generalization of this to Schwartz-Zippel lemma to be valid over rings. And it's a bilinear version. I have not been able to prove a generalized version. And so there is some open questions in the work, but I would be happy to talk to anyone who is interested in generalizing this further. The important thing to note here is that there is a slack here. And so this is sort of reminiscent from the speeds 2K, but it allows us to actually construct practical protocols. Finally, the protocol, very simple benchmarks actually show that this is very promising, particularly in the LAN setting for about, I would say, 10 to the power 3. That's the size, the batch size of these protocols. So since they are compute heavy, the scaling is in favor of other protocols, but this one, but usually nonlinear functions are applied in really small batch sizes, and that's why the protocol shines more in the smaller batch size as well as in the WAN setting. In the malicious protocol regime, like, you have slightly different scaling, but still it compares favorably with prior work. And finally, just to summarize, we have presented some constant round protocols. The generalization of Schwartz-Zippel lemma to rings could be interesting more broadly, but also enables semi-honest to malicious conversion, which could be of interest to other works. And finally, DPF approaches are known to be compute heavy. And so with work such as GPU assisted or hardware assisted secure computation, it might be more interesting to actually look into these protocols from a performance point of view. Thank you.